I'm posting this presentation as a continuation of the discussion of Fanno Flow that we had in the class. The material contained in these slides supplements what was covered in the class, and I would suggest that you make use of these also while you go through the topic. Before we start, in case you are listening to the audio, please make sure that you use headphones. Of course, this is not for a better experience for you, but rather to avoid a bitter experience for people around you. I don't think my voice will make a difference whether you use the headphone or hear it directly from the speaker. Of course, I am also trying to send across this PPT without the audio so that each time you want to see the materials, you don't have to put up with the voiceover. As I mentioned, the purpose of these slides, the material that is presented in these slides, is to conclude the analysis of Fanno Flow, which we have already started in the previous sessions in the class. And we know about the uncertainties that hover around. And in case we don't have more classes before the end semester examination, whenever it is going to be, I would expect, or I would suggest that you please go through these materials and be prepared with the material that is provided, the discussion that is provided in this set of slides. However, first and most important, please stay safe, stay away from the crowd, isolate yourself from the crowd, stay healthy in your respective abodes. Please don't get into any adventures. Your safety first. Nothing is more important than your health, not even compressible fluid flow. Now we get into a recap of what we have discussed in the class, the topics that we have already covered in the class. As we know, Fanno flow addresses one-dimensional steady flow inside a constant area depth, or it analyzes the coupling between compressibility and fluid friction under the assumptions of steady one-dimensional adiabatic flow in a constant area depth. We have already discussed in the class that in Fanno flow, in the analysis of Fanno flow, fluid friction is modeled as a resistive force, a resistive surface force, which is acting in a direction that is opposite to the direction of the flow. And we have also seen that, as you have studied in fluid mechanics, for engineering analysis, the friction is modeled by the parameter called friction factor F, which is non-dimensionalized as F equals tau W divided by half rho V squared, where tau W is the wall shear stress. We have also seen that the continuity and energy equations can be applied under these conditions, and we can consider, we can use the analysis, the conservation of mass and energy to arrive at relations for the ratios of temperature and static pressure. What we first did was to apply the energy equation, because we know that stagnation temperature is constant since we are considering an adiabatic case, and by the application of energy equations we have derived this relation that is shown on the top, T2 by T1, that is ratio of static temperature across the duct 2 and 1, the two sections that we are considering. And we have seen that it can be expressed as 2 plus gamma minus 1 m1 squared divided by 2 plus gamma minus 1 m2 squared. In fact, I guess we wrote that in a slightly different fashion in the class. I guess we wrote it as 1 plus gamma minus 1 by 2 m1 squared and 1 plus gamma minus 1 by 2 m2 squared, but you can note that it's the same expression. Similarly, we have combined it with the energy equation, with the continuity equation, and we have got a ratio for static. This derivation also we have done in the class, that is the ratio of static pressures P2 by P1 is equal to M1 by M2 square root of T2 by T1, and combining the expression for T2 by T1 we can now write it as P2 by P1 is equal to M1 by M2 multiplied by square root of the expression that we have for T2 by T1. We have also seen that in a similar fashion as we did for Rayleigh flow, usually the ratios can be written with respect to a sonic reference condition. That is, if the length were long enough, the flow would choke at some point, and if it were to choke, then at that point Mach number, the reference condition, the sonic condition, Mach number will be equal to 1, and in the above expression if we substitute for M2 is M2 as 1 and the respective properties are as marked by star, then we can write that T by T star is equal to gamma plus 1 divided by 2 plus gamma minus 1 M1 square, which comes directly from the equation that we have written earlier. Similarly, a ratio for P by P star which is equal to 1 by M square root of gamma plus 1 divided by 2 plus gamma minus 1 M squared. I just want to remind you about how we defined or how we conceptualize the reference location of sonic Mach number. Please look at the image. We have that solid length which typically is marked from 1 to 2, and then we have that the section that is marked by dotted lines, which is the extended length, the hypothetical extra length, which would potentially take the flow to sonic conditions. So at the end of that hypothetical section, we have, or we can visualize as the flow to be achieving Mach number equals 1. So these two relations that we have written here, T by T star and P by P star, are ratios of local static pressure or local static temperature as the case may be to the respective values at the sonic conditions. So we are expressing that these as a function of the local Mach number. So this much we have already done in the class, and so considered the interpretation of the conceptual extension of the deck to L star. And as I just mentioned, what I want to highlight here is that this length is also referred to as maximum length, L max. I guess I'll be explaining that more in another slide. So for now I'll just leave this part. We started in the class the application of moment. So what we discussed so far was continuity and energy equation. We have also attempted application of the momentum equation. We started off with the finite form of momentum equation, the familiar form that we have been using, and we have modeled the surface force as the wall shear multiplied by the peripheral area pi dl, and sticking to the representation of wall shear, we have it as pi dl multiplied by half rho v squared into friction factor. And for a differential control volume, we have already written it as dp plus d of rho u squared being equal to minus 4 by d tau w dx. This 4 by d, I don't remember whether we discussed that in the class, but you can see that if you do that yourself, you can see that the 4 by d on the right hand side comes due to the division of the area pi dl by the cross sectional area pi d squared by 4. The pressure differential, which is on the left hand side, dp etc., works on the or acts on the cross sectional area pi d squared by 4, whereas the friction force, the shear force, acts on the peripheral area pi dl. So when we normalize or when we divide it by the cross sectional area, the term that will be left on the right hand side will be 4 by d, which comes as the ratios of ratio of the two areas. Please also note that the left hand side here, dp plus d of rho u squared, can also be written as dp plus d of rho u multiplied by u, rho u and u being in the being inside the bracket. The convenience of writing like this is when you expand the differential, d of rho u is, as we know, is rho multiplied by velocity. Please note that in these slides, in fact, I used u as velocity. Please bear with that. In fact, we have been using v for velocity. I guess I missed the notation here, but please remember that we are using here u for velocity, not internal energy. So here rho u is nothing but rho v, that is which is constant, which means that d of rho u, when you expand the differential, d of rho u is going to be 0 because of continuity. That will simplify to the expression will simplify to dp plus rho u du is equal to minus 4 by d tau w dx. That's because d of rho u is equal to 0. So this the one which is highlighted here in red fonts is the differential form of momentum equation, and with some manipulation of velocity or relating velocity to Mach number, this can be, I have not done the derivation, the entire derivation here. I am just jumping to the final expression. Instead of velocity, if you write Mach number, the whole expression gets converted to 2 of 1 minus m squared by gamma m squared, etc. That long expression that you have in the box. Again, I apologize for mixing up the two notations u and v. Please be sure that in these slides, nowhere we are referring to internal energy. So wherever you see u, take it as v, consider it as v. You want, you can even correct it in your notes. It's v and not u. So don't confuse it with the internal energy. In this whole set of slides, we are not using internal energy at all. So wherever you see u, you please take it as the velocity v. Now, so we have this expression that is marked in the box here, in which on the right hand side you have the all important parameter 4 by d f dx, which is the representation of the force caused by friction. Now, when you have this, in fact, that's a non-dimensional parameter. So when you have this, strictly speaking, the fluid friction or the wall friction may vary across the length of the duct. Please keep in mind that we are going to apply this across the length of the duct. In real applications, though fluid friction may vary along the length, it's quite usual to use an average value for F, that is an average friction factor over the length. So usually F will be considered constant and will be represented as an average value for a specified length of the duct. Now this equation again can be integrated, and the integration is usually done with the limits of entry from entry. That is, keep in mind the flow is entering at some location into the duct and proceeding till the end of the length. Integration is done as the entry length or the entry location being L equals 0 and the hypothetical choking length as being L star. So from 0 to L star. So dx, the x varies from 0 to L star, and m varies from the local Mach number, the entry Mach number to the sonic Mach number. And under these conditions, the integration is also a fairly complex mathematical process. We are skipping that here and just writing the result of the integration here as 4FL star by D is equal to etc. It's a long expression which is in terms of Mach number. So this expression provides us with a tool which can be conveniently used. Conveniently because these values are tabulated as usual, as we have seen always in gas tables. So this expression can be used conveniently to calculate Mach number, to friction factor, to the choking length and the diameter of the duct under the assumptions that we have. We'll get to know the applicability or the utility of this expression as we proceed further. Before that, this fact I had emphasized earlier. I'm just re-emphasizing it here. L star, the choking length. This is in literature is also referred to as L max, the maximum length. This is because that's the maximum length that you can consider. The choking length is the maximum length that we can consider for a given set of flow conditions. If it is subsonic flow, that's the maximum length that you can give for given mass flow rate. So that's why sometimes people not use the notation of L max. What I want you to keep in mind is that what we call as L star and L max, what you see in the gas tables as L max are the same parameter. So it's the same choking length. In fact, the gas tables that we use of E. Radhakrishnan, the third edition, use L max in the table. So when you look at the tables, you will see it as L max. Keep in mind that that is nothing but the choking length L star. And you can see in the image shown below the explanation for L max, which is actually equal to L star. And even if our analysis is confined to a pipe of length L, I repeat that, even if our practical analysis is confined or is of interest to a length from 1 to 2, rather a length of L of the pipe, we will still use these relations, which is actually in terms of L star or L max, which includes the hypothetical extension of the pipe till the choking length. How do we make use of it, or how this kind of an hypothetical length is useful in the analysis? We are going to see soon in the next few slides. Before we attempt, or rather before we go into further analysis, I'll just summarize the solution procedure that is usually adapted in making calculations, making engineering calculations for Fanno flow conditions. Typically in problems, the exit Mach number, that is, you will have to consider a constant area duct, a given section, a given length of the constant area duct, and the exit Mach number is found out by relating it to L star and the entry Mach number M1. M1, that is the Mach number at the entrance to the pipe, will be usually given, and which can be used to calculate L1 star based on the expression that we have just seen. We can also use once we know the total length of the pipe, we can also calculate L2 star L2 star as L1 star minus L. Now what is L2 star? L2 star is from the same way as L1 star. L1 star means the length that you have from L1 till the choking section, the choking point. Similarly, L2 star is the length that you have from starting from L2, that is end of the pipe here, to the choking section. So I again repeat this fact. It doesn't mean that you always have the choking length, but if you were to have sufficiently long pipe to choke the flow, the length that would result is what we call as L max. So L2 max is the length. If you refer to the image again, the figure again, L2 max is the length from section 2, that is exit of the pipe, to the choking section. So the outlet Mach number M2, if you know L2 star, then from the tables we can work backward and get L2 star, the Mach number corresponding to M2. We'll demonstrate that soon, so it will be clear to you once we do that numerical example. Now the Fanno flow tables, I'm just introducing how they look like. Again, we refer to the gas tables of E. Radhakrishnan, third edition. You can see the image on the right hand side. As we have seen in all cases, you have the first column, which is Mach number, starting from low subsonic values and proceeding upwards. So you have Mach number in finite intervals. For each Mach number, you can see the ratios for T by T star, P by P star, P naught by P naught star, rho star by rho, F by S star, for FL max by D, etc. For FL max by D. Now, so these are parameters that are calculated based on the expression that we have seen already, based on the ratios that we have seen so far. Now, so these are just calculations, or the values based calculated based on the expressions that we have seen so far. Now, the most important thing to note here is the rightmost column, the last column, which shows 4FL max by D. Keep in mind, this also means 4L star by D. And this is the non-dimensionalized choking length for each Mach number. Obviously, it's a non-dimensional parameter, and it can be considered as a non-dimensional choking length for each Mach number. So, if you know M, you can calculate L max for a given value of D and F, and vice versa. Keep that in mind. If you know the value of M, then you can read, corresponding to that M, you can read the value of 4FL max by D, and in that, if you know F and D, then you can calculate L max. So if you know friction factor for the pipe and its diameter, you can find out what is the length it takes for a given Mach number to reach the sonic condition. Starting from a given entry Mach number to reach the sonic condition, how long does the pipe, or what should be the length of the pipe, and basically that is L max. So this is typical, and once we know all this, we can of course, once we know the Mach number, we can use other ratios, etc., which we will see when we work out that the numeric example. This is how the Fanno Flow tables are used. Please note that in Radhakrishan's table, I guess the page number is 113. Make sure that you are referring to gamma equals 1.4. That the name of the table is Fanno Flow, and I guess it starts as table 7.2. What is marked by red arrow here is the parameter that we defined here, just or we discussed just, that is for 4FL max by D. Before getting into the numerical example, we will also take a look at how Fanno flow is represented on a TS diagram. Again, TS diagram we are familiar from the discussion that we had already for Rayleigh flow. Again, it's a non-isentropic process. Keep in mind, the presence of friction renders the process non-isentropic, though we are considering adiabatic flow. So adiabatic flow through uniform area duct is, though the flow is adiabatic, it's still irreversible because of friction, and hence it's a non-isentropic process. Entropy varies. Now, if you were to do a similar analysis as we considered for Rayleigh flow, TS on the TS plane, that is on x-axis being for temperature, absolute temperature, and y-axis being for entropy, you will get a curve that is qualitatively similar to what is shown here. Now, please focus on the image. You can see that it can be considered as having an upward part and a lower part. Upper part, or the one that is corresponding to higher values of T, and the lower values of T, which are, when I say upper and lower, that is with respect to the point that is marked as M equals 1, the sonic condition. The upper part of the flow corresponds to subsonic flow. So when you have flow in the range, so in the Mach number range, say compressible, or in fact compressibility can be accounted much earlier than 0.3. So before Mach number equals 1, the flow properties vary as shown in the upper part, say like 1 to 2, that is from an arbitrary Mach number M1 to 2 M2, the flow variation will be represented as what you see there in the image. Similarly, the lower part of the flow represents supersonic flow, that is, say like 1 dash to 2 dash, or 1 dash to all the way to 1, M equals 1 is supersonic flow. So the upper side of Fanno flow pertains to subsonic flow, lower side of lower side of the Fanno flow curve represents supersonic flow. One thing that you will readily note is that the effect of friction on subsonic flow as well as supersonic flow is to take the flow to Mach 1. That is indicated by the blue arrows shown in the on the two sides. That is, in subsonic flow, the flow accelerates towards Mach 1. Supersonic flow, the flow decelerates towards Mach 1 as a result of friction. So what we readily conclude is that friction accelerates subsonic flow and friction decelerates supersonic flow. So if you have a Mach number, entry Mach number as say say 0.4, 0.5, it's quite possible that if you have a sufficiently long pipe duct, you can get at the end of the pipe, you may be able to get Mach numbers like 0.7, 0.8, etc. That is, flow accelerate just because the effect of friction in subsonic flow. Now, where does this energy come? It means that obviously when you say that flow is accelerating, it means that the kinetic energy is increasing. Where does it come from? It comes from the internal energy. So the temperature drops, rather the static temperature drops, but the velocity increases in subsonic flow. And quite the opposite happens in supersonic flow. Supersonic flow, as a result of friction, supersonic flow decelerates all the way to m equals 1. So and of course the static temperature increases. So these two observations, that is flow decelerates in the subsonic side, decelerates in the supersonic side, and accelerates in the subsonic side as a result of fluid friction. These two observations are important from the perspective of constant area duct flows with friction. Please also note that these two arrows that you have there are the only possible directions in which flow can take place. That is, in Rayleigh flow, if you remember, in fact I have another slide to remind you about how it looked like. In Rayleigh flow, you had an opposite arrow also. That is, on each side we marked a heating direction and a cooling direction. In the cooling direction, the opposite happened. Here, you have only one direction. For example, in subsonic flow, there is only one way the flow can proceed, and that is towards Mach 1, and that is by acceleration to Mach 1. And similarly, on the supersonic side, the only effect the friction can have is to decelerate the flow. Flow in the other direction is not possible, and it should be quite obvious from the TS diagram why we cannot have the flow in the reverse direction. That's you can just examine the figure and see that if you were to have flow in the opposite direction, that would mean that, I'm just pausing so that you can find out what does it violate. On both sides, if you were to have flow in the opposite direction, you can see that the entropy will be reducing, and it's a frictional flow. That is, it's an irreversible flow. In irreversible flow, that is, in flow with friction, you cannot have entropy reducing. The flow can only have increase in entropy as a result of the flow. Keep in mind, in Rayleigh flow we could have a drop in entropy. That is because it's a cooling process. As a cooling process, so the entropy of the system reduces, that of the universe increases, etc. So, and the net entropy in real processes increase, and whatever you have studied in thermodynamics. But here in friction flows, in flows with friction, you don't have that analogy of cooling. So the only effect that you can have, only effect that friction can have, is to have an increasing direction of entropy. So it's not possible to get across the curve even theoretically. In fact, when we discussed Rayleigh flow, we mentioned that a theoretical possibility exists of cooling the subsonic flow and reaching it to the sonic Mach number, and then reversing the direction of heat transfer, and then taking it to the supersonic side, etc. Rather, heating the supersonic flow, heating the subsonic flow, and then reversing it, etc. That kind of a possibility, even theoretically, does not exist in Fanno flow. A Fanno flow, you cannot have the flow along the same curve being going across the sonic point. Now, other parameters: static pressure decreases due to friction in subsonic flow, where velocity increases. Static pressure increases due to friction in supersonic flow, where the velocity decreases. Keep in mind, in subsonic flow, the velocity increases, static pressure decreases. In supersonic flow, the velocity drops, the velocity decreases, and static pressure increases. And most importantly, in both cases, whether supersonic or subsonic, stagnation pressure decreases due to friction. Decreases due to friction. So friction, the only effect of friction on stagnation pressure is to reduce it, because friction is a dissipative process. It is where energy, which involves dissipation of energy, and that invariably leads to a drop in stagnation pressure. So whether you are operating on the subsonic side or supersonic side, the stagnation pressure is bound to drop as an effect of friction. Comparison of the curves, or rather the appearance of them for Rayleigh flow and Fanno flow. On the left hand side you have Fanno flow curve, which we have just discussed, and on the right hand side you have the Rayleigh flow curve. We readily notice that you have two sides that are marked by or demarcated by the sonic condition. In the Fanno flow, of course, keep in mind that T naught is constant. So for any point, any local section 1, M1, or rather any section 1, section 2, etc., if you were to determine the stagnation temperature, it will be the same, because it's an adiabatic case. Fanno flow is adiabatic, stagnation temperature does not change. Rayleigh flow is non-adiabatic, stagnation temperature keeps changing as a result of heating or cooling, whatever be the case. So this is how the two curves look or compare with each other, their qualitative appearance with each other. We have discussed Rayleigh flow curve already in detail in the class, and we have now seen the behavior of Fanno flow curve also. Now with that, we consider a numerical problem. Here you have air flowing in an adiabatic pipe, a pipe which is the walls are insulated, so there is no heat transfer, no cooling, no heating. Diameter of the pipe is given as 10 centimeter, and its length is specified as 61.2 meters. So fairly long pipe considering its low diameter. The static pressure and temperature at the inlet to the pipe are specified as 550 kilopascals and 350 Kelvin respectively. The inlet velocity is 75 meter per second, and the pipe has an average friction factor. Average friction factor. Please remember that as we have already seen, friction, though it may vary across the length, is quite natural, or is quite usual to use an average friction factor which is constant, and here it is given as 0.0055. The two questions: one, first we have to determine whether the flow gets choked at the exit of the pipe, and the second, calculate the Mach number and the static pressure at the exit of the pipe. I'm just repeating this slide which we have discussed already as solution procedure. As I mentioned in that part of the presentation, typically Mach number 2, that is Mach number at the exit section, can be determined by can be found by determining the L star, that is the choking length L star or L max, based on the inlet Mach number M1. Once we know L1 star based on M1, we have seen the gas tables already. M1 will help us determine L1 star because F and D are already provided. So M1 will help us find out L1 star. We also know the length of the pipe, that is the actual length of the pipe, 61.2 or whatever is mentioned in the problem. So L is provided as 61.2. L1 star we can find out as a function of M1, and if you do that, then using this expression you can just see L2 star is L1 star minus L. That comes obviously from the geometry of the figure. You can just look into the figure. Of course, I have, in the expression I have written it as star using star, but here it is L max in the image. Both are the same. So L2 max is nothing but L1 max minus L. L2 max is equal to L1 max minus L, as you can readily see from the image. Which means that if you know L and L1 max or L and L1 star, you can calculate L2 max or L2 star. Once you know L2 star, you can go back to the table and correspondingly get the value of M2. So that's how you determine the exit Mach number. Coming back to the problem, first we determine the entry Mach number. The inlet velocity is given 75 meter per second or whatever, and inlet temperature is given, so we can readily get V1 by square root of gamma RT1 as 0.2. So the inlet Mach number is 0.2. Now we get into the tables, gas tables. We can see that corresponding to 0.2, the 4FL max by D parameter, that is 4FL max by D corresponding to 0.2 is around 14.533, which is nothing. So from that we can calculate L max, which is equal to L star, because we know F, we know D. So from 4FL max by D we can substitute these values and get the value of L star, that is the choking length corresponding to the entry Mach number of 0.2. We get it as 66.04 meter. I guess I missed out the dimension there. 66.04 meter, and so which means that corresponding to the inlet conditions of 0.2, you need a pipe as long as 66.04 meter so that you can reach the choking length. Whereas here the given length is 61.2 meter, which means that the flow is not choked at the exit of the pipe, because the exit is at 60, the real exit, the physical exit is at 61.2, whereas choking is at 66.4. So since the duct is not long enough, choking does not happen at the exit of the given section of the pipe. So that answers the first part. Now for the second part, we know that for the given pipe L is equal to 61.2, and the so we can as you have just seen in the previous slide, the choking length corresponding to the second section L2 star can be written as L1 star minus L, which happens to be 4.84 meters, which means that for the exit section the 4L Fel max by D, which we can calculate now because we know the L max corresponding to the section, the exit section. So we can calculate 4FL max by D by substituting the values for F, L max and the given value of diameter, etc. So we get the parameter as 1.0648. Now we get back to the tables. Corresponding to 4FL max by D, we read what is the corresponding Mach number. Please note what we are doing now. We have actually calculated corresponding to the exit Mach number what is going to be the choking length. Now and based on that we have calculated what is going to be the 4FL max by D. So we are using this 4FL max by D in the table to read the corresponding Mach number, which is nothing but M2 here. So M2 that comes to be approximately equal to, with the accuracy that we have in the tables, that comes to be something like 0.5. So that answers I guess that contributes to the second part of the answer, that is Mach number at the exit is 0.5. Now based on P1 by P star, that is based on M1, we can calculate P1 by P star from the table again, that is M1 is equal to 0.2. We can readily read the value for P1 by P star, which is 5.455, which gives us P star because P1 is known. So P star, the static pressure at the choking section. Keep in mind the choking section is common for M1 and M2. So static pressure at the choking section is 100.82 kilopascals. Now since we know M2 already 0.5, we can calculate P2 by P star, or rather we can read P2 by P star from the table, and that happens to be 2.1381. Again, we know P star, which we have already calculated. So P2 can be calculated from this ratio as P star multiplied by 2.1381, which is equal to 2.56 kilopascals. So static pressure at the exit of the pipe is 215.56 kilopascals. Please note two things. One is Mach number has increased. It's a subsonic flow because entry Mach number is 0.2. So it's subsonic flow, and inlet Mach number is 0.2, exit Mach number is 0.5. So you have an acceleration. So subsonic side we have an acceleration from M1 to M2, that is 0.2 to 0.5. Similarly, the static pressure has dropped from the inlet value of I don't remember what was the inlet, 350, whatever. From the inlet value, there is a drop in static pressure, and that comes out to be at the exit of the pipe. The static pressure happens to be 215.56. So there is a drop in static pressure, there is an increase in Mach number, and these are consistent with the observations or the remarks that we made based on the TS diagram of the flow. So this is typically how Fanno flow problems are solved. You use the conceptual extension length that corresponds to Lmax and calculate back the values corresponding to the exit section for a set of values given for the entrance to the pipe. With that, ladies and gentlemen, I wind up the course. With all the uncertainties that hover around, in case we don't have additional or any more instruction days this semester, you can consider this as the concluding session for this course. I thank you all for the interest that you have shown in the subject. All through the course, participation of this class has been quite good, live and inspiring. I thank you all for the same. I wish you all the best in the end semester examinations, and I repeat, please stay safe, stay healthy and isolated from the crowd wherever you are. Wish you all the best. Goodbye.